So one of the important properties of signals is the periodicity of a signal. So when we say a signal is periodic, what we mean is that the signal's value will repeat after some time duration, and we call this time duration as the period of the signal. So this period is some time duration t, which is actually finite. So after a finite amount of time, if the value of the signal keeps reappearing again and again, then we say that that particular signal is a periodic signal. So let's take a simple example and then observe it through that. The most famous example that we know of a periodic signal is the cosine signal or the sinusoid, either the sine or cosine, whichever you want. So let's observe the cosine signal first, cos omega t. So how does this look like? So this signal, so we know that the signal keeps repeating after every 2 pi radians. So what do we mean by that? That means that the signal, if it starts at time t is equal to 0, then after some point of time it will start repeating itself. So if you observe this window in this time, in this case the period t is in fact equal to 2 pi by omega, where omega is the angular frequency. So after this time duration, the signal keeps repeating itself. What do we mean by that? So if the value of the signal at t equal to 0 is, let's say, 1, then after capital T seconds, in this case 2 pi by omega, the signal's value is 1 again, which makes sense because cos of omega t plus capital T here, what is that? That is equal to cos of omega t plus omega times 2 pi by omega, which is basically 2 pi. Cos of theta plus 2 pi is cos theta itself. So this is cos omega t. So one thing, if you notice here, we did not fix any value of time. So no matter what value of time that you pick, so you can start at this point and add plus t to it, the same value of the signal keeps repeating again. So you can take this point, the value of the signal here is 0 because it is cos of pi by 2. Now add plus t to it, and the signal keeps repeating. So it doesn't matter at which point you observe the signal, as long as you add plus t, you will start observing the same point. This is what we mean by periodicity. That is, any signal that satisfies this property, that x of t plus capital T is equal to x of t itself. That is, the value of the signal after capital T seconds is exactly the same, then we say that that signal is a periodic signal. Now one thing that if you observe here, now what if we try to compute cos of t plus nt, where n is some integer, okay? What we mean by integer is n is equal to some plus or minus 1 or plus or minus 2 plus or minus 3. This is what we mean by integer. Now let's observe what happens here. The same thing is what we will see, plus omega times n 2 pi by omega. So now cos of theta plus 2n pi is also cos theta, which means this is also cos omega t. So if we multiply this capital T with 2 or 3 or 4 or 5, it still satisfies the same property. So which means in this particular example, let us say omega is equal to 1. If omega is equal to 1, then the period of this particular cosine signal is equal to 2 pi for omega is equal to 1. So you will observe that the signal will keep repeating itself for 2 pi seconds or 4 pi seconds or 6 pi seconds or 8 pi seconds and so on. Then how do we say what is the period? We'll say that the fundamental period is the amount of time which is the smallest value required for the signal to keep repeating itself. That is, the smallest value of time t such that this condition is satisfied is what we'll refer to as the fundamental period, and that is what we'll call as the period of the signal. Okay. Of course, the signal will also repeat itself for all integral multiples of the fundamental period. So if you take this cosine signal, it will repeat again and again for every 4 pi, 6 pi, 8 pi and so on. But there is one fundamental period, and this is the same for every periodic signals. For example, you take this case here, okay, this signal keeps repeating itself. So here the signal has a period of 6 seconds. So for every 6 seconds, if you take the value here, after plus 6 it will repeat itself, after minus 6 it will still be the same. So it will go on either sides. So the signal will keep repeating itself after every capital T seconds, and that will be the period of this. Now another nice important property is not just the value, but the area of the signal itself keeps repeating again and again. That makes sense because the value of the signal repeats, which means if I integrate the signal in one period, that is compute the area under the signal in one period, it should also keep repeating itself, right? Because the signal value itself is repeating. So the area under the period will also be the same because the values are anyway the same. So that's what the second property says, or the second condition that is given here. It's simply saying that it doesn't matter where you start the period of integration, as long as the period of integration is some integral multiple of the period. That is, here you are integrating in this interval a to a plus nt, and here you are integrating from b to b plus nt. It doesn't really matter what the value of a and what the value of b is, as long as the duration or the interval's length here is nt, which is the same here nt, both will have the same value. That is, the area under the curve, as long as you are integrating it for some integer multiple of the period, will always produce the same value irrespective of where you start. For example, if you take this cosine signal, you can start integrating the signal from, let's say, this point, from this point to this point, right, in this region. This will give the same area as integrating the signal from, let us say, this portion till this portion. So where you start does not matter, but the length over which you are computing this area, as long as it is some integer multiple of the period, then you will get the area to be the same. So this is another property of the periodic signal, which we will use it later for very interesting applications. Okay, now when do we say something is aperiodic? That's just the reverse of the case that we just saw, which means a signal whose value does not repeat, right? So if the signal values repeat after some capital T seconds, then we say that it's a periodic signal. So if the signal's value never repeat, no matter whatever is the value of capital T that you choose, then you say that it is an aperiodic signal. A very simple example is a finite duration signal. What do we mean by a finite duration signal? Any signal that is non-zero only for a finite amount of time. For example, let's take this signal. Okay, let's say this is -1, this is +1, this is 1.5, and let's say this is 2. And all other places it is 0. So this is a finite duration signal, which means the signal's value is non-zero only within the interval -1 to 2. Everywhere else it is 0. So clearly this is an aperiodic signal because this value never repeats. The value that is present here once never repeats again. Okay, and let's see another example. So let's say we observe a sinusoid. So let us say it is 0 till t is equal to 0, and then it completes, let's say, 3 cycles, and then it becomes 0 again. And in this 3 cycles, it exactly follows, let's say, sine omega t. Is this signal periodic? No, it is not periodic. It is an aperiodic signal because there is a portion of time where it is completely 0, and it looks like a sinusoid only in a very small finite portion of time. Okay, only in this duration it looks like a sinusoid. So if I try to see if it satisfies this condition, then let us see what is the value of the signal at, let's say, t is equal to -1. At t is equal to -1, the signal's value is 0. Now let us set capital T is equal to some 2 pi by omega. If I set capital T is equal to 2 pi by omega, then small t plus capital T is somewhere here. Right? Let us say this point is on. So this is t is equal to -1 and this is t plus t. It is -1 plus 2 pi omega. So clearly the signal's value at this point and these points, so the 2 points that are under consideration here, are not the same. So it does not satisfy this condition, which necessarily makes this an aperiodic signal. So even though for a small window of the signal it may look like periodic, if the overall signal is not periodic, if it does not satisfy this condition, then it is still an aperiodic signal. Okay. So if you think about it, this condition necessarily means every periodic signal should extend from -infinity to +infinity, because this capital T can be anything and the small t can be anything, which means the small t can be as small as 0, or the small t can be negative, or it can be as big as 1 billion seconds or 1 trillion seconds. So no matter what is the value of the time that you plug in there, for every value of time it should satisfy this condition, right? If it satisfies this condition, then it necessarily means the signal has to extend from -infinity to +infinity, because then it's an infinitely long signal. Every periodic signal, mathematically at least, has to be infinitely long in length. But we know that all practical signals are finite length signals. So if all practical lengths are finite length signals, then do we not have periodic signals at all in real life? If you think about it, let's say I have a circuit. I will turn on the circuit today, and let's say it runs for 10 minutes or 1 day, or even if it is running for 20 years, that is still a finite length duration. So we can observe a signal only for a finite length duration. So if we are observing signal only for a finite length duration, are we saying that in real life periodic signals will never exist? Well, what we are going to do is, in real life we will say that there is a duration of interest, and in the duration of interest, as long as the signal satisfies this property, we will say that it is periodic. Technically it is still aperiodic because the small t has to extend from -infinity to +infinity. But what we are going to do in real life is that our duration of interest is some amount of time, some interval, and in that interval, as long as this condition is satisfied, we will say that the signal is still periodic. So this is the condition that we will use when we are analyzing practical circuits. When we take a practical circuit and then say that, okay, I am going to assume this signal is periodic, then it means that for the entire duration for which the circuit is on and working, we will assume that the signal that is periodic will satisfy this condition. Okay. So let us see some examples now.